There we go. All right. All right. So with that, taken care of, the first thing I'm going to do is to go back to the previous lecture because it has been a week, since we talked about the actual topics. So we're going to go back to the videos. And 1 week ago, today is the third, is the first. So 1 week ago is the 24th, right? Or is it the 23rd? 7 days ago. Yep, I think this is the one. Okay, you guys cannot hear anything because it's all in my ear. But that's the lecture. Oh, okay. So it's the one on Monday. So that means we're looking at this one. That's a Tuesday, Thursday, but I think it's the same time frame. And I think we did something like this. We analyzed the circuit. Yep. Okay. Yeah, I just wanted the confirmation. So that is correct. All right. So, hmm? Oh, you like it? Well, you're gonna like what we're gonna do today too, then. It's a little bit more of that. Okay. So we can go back to this note here. Okay. And I'm just looking to make sure that I'm recording. And we are recording. All right. So with that, the next memory device is called a D flip-flop. So this is kind of like the text representation of a D flip-flop. I'll go ahead and construct it in Logisim just so that you guys can see what it looks like, and also how this text description is describing the structure of the circuit, even though it doesn't look graphical to us. Okay, so let me go ahead and start Logisim because I think this is going to be a useful experience. Logisim, there we go. And it always starts on my other screen, my other monitor, so it's okay. Bring it back here. There we go. All right. So the first thing we need to do is to take a look at all the components. So this is similar to object-oriented programming, where not NAND2, SR latch, input pin, and output pin, because they all start with uppercase letters. So these are basically classes. They are the type of things that we need. And then these are quote unquote the objects or variables. So N is a NOT gate, N1 is a NAND2 gate, NAND2 is a NAND2 gate, and so on. So here we're using the SR latch as its own unit, okay? We just call it SR. We have two input pins, one is D for data, and then one is EN for enable. And then we have two output pins, same two output pins that we usually do, which is Q and NQ. So this portion describes what components do we have in the circuit and how the components are named. This portion, on the other hand, is basically saying, okay, each line is adding a single node to the circuit, and a node is made out of connections. So that means, this is one of the connections where the node needs to go. This is another point or another port of a component where the node needs to go, and this is the last one in this case. So one thing you can do if you think this is a little bit confusing is to go back to the SR latch because there's also a text description of the SR latch itself over here, and the naming is consistent with the circuit that we were working on Monday. All right. So this is really kind of important. It's a transition to how we use Logisim graphically to display a circuit, and instead now we are using these quote unquote statements to describe a circuit. So the first thing is why, right? You might have noticed that I asked that question a lot, okay? Because it really is important. So why do you think why do you think it is useful to shift from a graphical representation of a circuit to a text representation of a circuit? I'll give you a hint. Flowcharts versus C++ code. Okay? How do those two compare? Go ahead. Okay. So it's not as visual, okay, but to people who are experienced in programming, it can be quote unquote visual. So, but it has more density for one, right? In order to specify a circuit that is a little bit more complex, the text representation is not a whole lot more compared to the previous circuit, but the graphical representation, as we'll see, is a little bit more complex compared to the one that we saw earlier. Well, the main difference is if you are to use flow charting to write all your programs in Cisp 360, do you think it's going to take you a little bit longer in order to get those pictures right and have all those arrows going to the right places? And then when you have to debug it, that's the worst place, right? That's the worst time because what do you have to do in order to say, oh, I need two more statements between these two? You have to move everything around and give you the extra space, put that stuff in, break some of the existing connections so that they connect to the new blocks, and then reestablish the connections from the new blocks to the old blocks, right? So it's a lot more cumbersome when it comes to editing, but the worst part is the graphical representation cannot really be easily used to represent abstraction. So what is an abstraction? The abstraction here is, oh, I'm not going to draw out the entire SR latch anymore. It is just seen as a single component in this case. Is that okay? All right. And pragmatically speaking, it is also important, especially for people who are at least considering going to Berkeley, because this is the kind of language that you need to learn in their final year project in their computer science program. Okay, because you'll be specifying the logic inside an actual industry processor. That's not going to be simple like the one that we are working with here. So that means if we are to use logisim to represent that kind of logic, it'll be like really busy. Okay, it will be really busy and difficult to navigate and understand. But in text representation, it's not so bad because for things that you need to have multiple copies of, you can actually set up quote unquote a loop to do it. If you know the structure of how a whole bunch of stuff that are replications of each other and you know how they're supposed to be connected structurally, you can use code to represent it. So that means you do not need to draw a bazillion gates and specify how they connect. You can write code to do that. Okay? So that's the main reason why I want to introduce this way of looking at a circuit because it is a much more compact representation, easier to edit, and also this is what people in industry use. Not specifically this language because this is actually just borrowed from C++, but that's because I know you guys have some experience with C++ from CISP 360. So with that all said, we are going to kind of construct the circuit. Okay, so I'll do the usual thing. Okay, you copy and paste this portion into a display here. Make it always on top. This is a little bit bigger than I want, but I think we can make it work. All right, so we switch back to Logisim, and then the first thing we need to do is to add a SR uh, latch circuit. So this is a SR latch as a type, and you can see how what you're creating in a circuit, it is really analogous to a function or a class in this case. Okay, so I'm actually creating a class that specifies the behavior of a circuit. So this is from from the previous class from Monday. We are just constructing something based on what we know about a SR latch. So we'll go ahead and specify NAND gate, make it narrow, two input. I mean, this is all stuff that we did the other day. So nothing new so far. Okay, duplicate that, put it here, like so. This goes to one of the two inputs. This goes to the other of the inputs, and then we have the crisscrossing. Okay, so the crisscrossing means this one goes here, and then this one goes to the opposite, which is here. So now we have an SR latch. Okay, so this is what the SR latch looks like. And now we can go back to the main circuit, which is trying to do this. So to implement this, then we say, okay, what do we need? Well, it looks like we need one single NOT gate here, and I'm going to use the label to say this is N, which is consistent with this variable N here. We need two NAND 2 gates, okay? So we're going to go pick up those two NAND 2 gates. So I'm going to go here and pick up these two, copy, and paste. There we go. So now we just have to name these two. One is N1, okay, N1, and the other one is N2, like so. And we need to pick up a single SR latch. So we go to the new type that we just created, drag it here, and then call this one SR because that's the name of the circuit. They are not labeled because SR versus Q and Q. I can remember the positioning of the pins, so we're good over there. We need two input pins, D and NEN. So this is our D, which stands for data, and this is our EN. Oh, okay, I forgot to press the enter key. P D, that's for data. And now we have the two output pins. One is called Q, which is the non-negated output, and then the other one is called NQ, which is the negated output. There we go. All right. So now we need to figure out, how everything is supposed to be connected using the node connectivity part. So now we put, kind of, okay, I know how to do. Move this up a little bit like that. There we go. All right, so according to this D dot pin, okay, the D data pin here, this port is supposed to connect to the first input pin of N1, and is also supposed to go to the NOT gate, the only input of the NOT gate. Okay, so I'm just gonna space out the pins a little bit so I get more room in between. Okay, there we go. The SR latch is gonna be here, and we need D to hook up to N. So I'm just trying to make it look nicer. Okay, so we can put N over here, and then N1 is going to be over here. I think that's going to be okay. So this goes to the first input of the input ports, okay, according to this. But it also goes to the input or the only input of the negation gate or the NOT gate. So it goes here. That's one node. So I'm just going to pause here and see if there are any questions about the terminology that I was just using. What is a component? What is a port? What is a node? So do we have any questions about those? Nope. Okay. All right. So we can move on to the next row here. Okay. It talks about how the EN pin is supposed to connect to the other input of N1. Okay. So that gets a little bit dicey. Okay, but we can make it work. Yeah. There we go. It goes also to N1.in0. Okay, so we just have to put it here, go like, okay, that connects here. There we go. Excellent. So now we go to the third row. The third row says, N.out, which is, the output of the NOT gate, goes to the second input of N2. Okay, so with this one, I just have to be careful when I cross over the other wire to make sure it is not accidentally connected. All right, so what else do we need to do? N1.out go to SR.S. Okay, so that's a pretty straightforward connection, like so. N2.out go to SR.R. Okay, so that's also pretty straightforward, like so. And then we just connect the output of the SR latch, Q to Q, NQ to NQ. So the top one is Q, it goes to Q here, and then the bottom is NQ, it goes to NQ over here. So there we go. Okay, so this is the actual circuit corresponding to the text that is in the reading material. Do we have any questions about how I use the text representation to come up with the actual Logisim circuit? No questions? Okay, all right. Now, I do want to emphasize that your next exam will have things like this, where I give you the description of the circuit, but only in this form. So that means you need to know how to read the specification of a circuit in text representation in order to actually see how things are supposed to be connected. Are we good so far? Because I just want to emphasize that when people are listening to this and go like, oh, okay, this is not going to be useful. No, this is going to be useful. All right, so with that said, I can now get rid of. Okay, first I need to move. I can just close it. All right, so I'm just closing the other bitmap here. So now the question is, what does this do? Well, D is data, En is enable. So what enable is enabling is, oh, should the SR latch remember the state of the D pin? That is what it's enabling. Okay, so right now En is a 0, right? So it's not enabled, which means if I toggle D over and over again, nothing happens to the output. And by the way, why is the output red? I thought red is bad and why didn't you fix that? The answer is it is it's not bad in the sense that we just don't know what it is. Okay, so but why don't we know what it is? Because the SR latch was set up with both inputs being ones to begin with. Okay, so what does it mean when both inputs of the SR latch, both the S and the R, are ones? It holds the content exactly. It means no change. Then you go like, okay, but no change from what? And the answer is we don't know because we did not initialize the SR latch. We have no idea what it was, okay, what the outputs used to be. We know that it is consistent in some way, okay, it's either the output is either 1 and a 0 or 0 and a 1, but we don't know which way it is, okay? So Logisim is actually smart enough to understand that and go like, okay, I'm just going to report we have no idea what it is. All right? So now we're going to go like, okay, so according to what you just said, Tag, if I click enable here, then the SR latch would actually listen to the D port here, so that whatever the D port has is going to be reflected to the Q port over here. That is what enable is trying to do, is to say, should I mirror, okay, from the perspective of the D flip-flop, the EN, the enable pin, is asking, should we mirror the input pin D data to the output pin Q, which is reporting the state of the D flip-flop. Okay, that's what the EN is trying to say. So that means if I were to click here to enable the D flip-flop here, then this pin would become a 1 and this pin would become a 0. Okay, so yep, that's exactly what it is. So now the question is, while it is still enabled, if I were to flip this D to a 0, what is going to happen to the circuit? That is a two-level question, okay? The first level of the question is simply, oh, okay, we are doing this in Logisim. If I just toggle D from a 1 to a 0, what is going to happen? That's a very easy question to answer because you just do it, right? So according to what I just said, which is the EN pin is asking, should we mirror the state of the D input pin to the Q output pin? Well, if that is true, that means if if I toggle the data pin right now, it is still enabled. We should see the output Q to change, quote unquote, instantaneously to the same as the D pin, which is going to be 0. Okay, so we can do the experiment. Okay, done. Oh, cool, it works. And you can test it a little bit more. You can say, okay, what if I were to disable the circuit first? And then I just play around with the D pin. Nothing happens to the output as expected, right? Because my description of how the circuit is supposed to behave is visible in Logisim. That's the first level of the question. The second level of the question is, how does it do it? Okay, so what do you think is going to be helpful to understand how it gets this done? The NCPD analysis. Okay, so what this means is even if I don't give you a homework assignment on this, okay, it would be tremendously useful if you are to go through a few steps like what we did today, but not using Logisim, but using the PD NC traces so that you can see, oh, okay, so I can now see internally this is affected first, and then we affect that, and then we affect that, and so on. Okay, so I'm not giving you an actual assignment that I would grade, okay, but I'm telling you that it would be very helpful for you to go through that exercise. Are we doing okay so far? All right. Okay. Just double checking, make sure my recording is still on. All right. So this is what we call a level sensitive D flip-flop, which means there are different types of D flip-flop. Okay. The next one is called edge sensitive D flip-flop. Now this one is really kind of interesting. So we'll go ahead and construct a circuit, and then we'll take a look at, oh, how is this kind of cool compared to the previous one? This one is cool in a different way. All right, so we will switch back. So I'm going to take a snapshot of this so that we can create the circuit, and then we will switch back to, and now we switch back to Logisim, just so that we can kind of create a circuit. So we click that, switch back to Logisim, and then we will continue with this one here, except I'm just going to change the original circuit to a level sensitive D flip-flop. And then the new one that I'm creating right now is going to be called the edge sensitive D flip-flop, edge sensitive D flip-flop. There we go. All right, so same deal, okay? We just look at all of these things and go like, okay, let's make those parts. Okay, we got two input pins. One is called CLK for clock, and then one is data, which is also D. Okay, so if you want to just use D, that's fine. And then the output pins would be just Q in this case. So we don't even bother to use NQ, okay, because NQ is just the negation of Q. All right, so what else do we need? We need two SR latches in this case. So we go to SR latch and we go like, okay, here's one. We label that what, S, okay. And then we have another one called C. Okay, so we put another one, call this one C. So this circuit is a little bit more complex compared to the previous one, but what it can do is also a little bit interesting. Okay, so we have two NAND gates. One is N1 and one is N2, but they're different. N1 is one that has three inputs, N2 is one that has only two inputs. So now we go to the gates. We go to NAND gate and then pull two of those. I suppose I can just go back to the previous circuit and just copy and paste it here, but too late for that. There we go. Duplicate. Okay, one of these I need to change it to have three inputs. There we go. And then the one that has three inputs is N1. Okay, so we just say this is N1. And then the other one is N2. All right, so I think we have all the components because we have 1, 2, 3, 4, 5, 6, 7. We have 7 components in the text representation, and we have exactly 7 components in the actual circuit. So now we're gonna create the actual circuit. Okay, so the first thing is I'm gonna move things around a little bit just so that I have enough room without having to get rid of that text description here. Okay, so Q can go here. All right, so the way I do the board layout is to look at the edges of the circuit, which are the inputs and the outputs, and then start to place components based on that first. So in other words, because Q only has one single port, so I want to see whose output is going to Q. According to the text description, it's the last node that we are adding. C.Q goes to the output pin Q. So from the perspective of, oh, I want the circuit to look nice, it's kind of nice to arrange it like this. Okay, so these two can kind of hang out at this little corner here. Okay, nobody else is going to bother them. All right, so we took care of this node right now. And then we look at the inputs. Okay, so we look at the input pins CLK. So CLK goes to S.R. It also goes to N1.in1. So we'll just kind of try to do a little bit of alignment, okay, just so that it potentially looks a little better. Um, all right, so let's do this. Okay, C goes to input 1, which is the middle one. Or is it the middle one? Yep, it is right here. So it is the middle one. But it also goes to the other SR latch, which is here. And it goes to S dot R, which is the second pin here. Okay, there we go. And now we go to the other input pin, which is D. So you can see how D is connected to only one input port, which is the middle one of N2, or the last one of N2, I should say. So we put N2 over here and say this one connects to here. Okay. So now we have taken care of that. So data pin is done. I mean, if you are doing this on the piece of paper, you can just kind of cross out or put a little star so that you remember which ones are done. So now we move on to the third one. Okay, N2 out, which is here, connects to N1 into. So into is over here. So this is, we have to wrap around a little bit. It's okay, not a big deal. There we go. All right, so it also goes to S dot S, which is this connection here. So, um, so we are looking at N2 going to S dot S. Okay, all right, there we go. All right, what about this one? It takes the output of N1 and it connects it to the first input of N2, but also C dot R. Okay, C dot R is right here. Okay, that's kind of handy. We're already in that neighborhood. Um, right, this one. So we also want to connect it to the first input of N2, which is this one over here. Okay. Eh, I can do it. It's just it will look a little bit on the ugly side, but it's okay. There we go. And then we have, well, we have these two pins not connected. So that is, oh, I think I forgot about C dot S, which is the next one. Okay, great. So S dot NQ, this is S dot NQ, is connecting to both C dot S and also the first input of N1. Okay, so we just kind of route this one. Oof, too much, but it'll work around here. And now we have an edge sensitive D flip flop. Okay, so a sanity check is to make sure all the input pins are connected to some kind of output. So when you look at all the input pins, okay, N1 has 3 input pins, they're all connected. N2 has 2 input pins, they're all connected. S as an SR latch has 2 input pins, they're both connected too. And then C also has 2 input pins, and they're also all connected too. So from that perspective, the sanity check is working. Okay, everything kind of checks out. But somebody's going to point out and go like, but what about this? S dot S is not connected. So yes, I did miss that. Okay, so N2 dot, no. This is not S2 S dot S. This is S dot Q. So when you look at the text here, S dot Q does not go anywhere. Okay, so we can just kind of, we can let the output dangling, but we cannot let inputs dangling. Because when the input is dangling, then it sometimes it is a 1, sometimes it's a 0, so your circuit will just do different things whether somebody is microwaving something near it or not. Okay, and that is usually not a good thing unless you're making a random generator that says, I will generate a random number, but only when the microwave is going. That also makes it not very useful. All right. So now the question is, what does the circuit do? Well, let me go back a little bit. Okay, if we really want to, which takes a little bit of time in this class, I can do the PD NC analysis of this circuit. Okay, and it's going to be more complex with this one. Okay, so we can do so maybe in the next class. But right now, the focus is What does it do as a whole? In other words, if I don't care about what is inside, what does it do? Well, what it does is kind of interesting. Instead of being level sensitive, it is now called edge sensitive. So the clock is the one that is providing basically, quote unquote, an edge, or it's sensing whether there's an edge. This particular circuit is rising edge sensitive, which means when clock goes from 0 to 1, that moment is when the circuit goes like, okay, what do I need to do? Okay. But for all other moments, the circuit goes like, oh, I'm just dozing off, taking a break. Okay. So remember that. Okay. That's important. That is really important. Okay. It's only when the clock goes from 0 to 1 that the circuit wakes up and do one thing. What it does when it does wake up is the same thing that the other D flip flop is doing. It is just copying the state of the D input pin to the Q output pin. So that's what it does when it wakes up. Okay, at that moment that it wakes up, that's the only thing it does, and then it goes back to sleep. Are we good so far? So you can see how the clock pin is not doing anything right now. It is at a static 0. So that means, oh, I can just toggle the D pin all day long and nothing happens. Okay, well, that's kind of the way we expect it. So this time, let's just say that the D pin has a value of 1 at the moment, okay, at the very short moment when the clock pin goes from 0 to 1. It is now a 0, and we go like, now it's a 1. So right at that moment, okay, the circuit wakes up and go like, oh, what? Oh, right, I'm supposed to copy the D pin to the Q pin. That's that one thing, and then went back to sleep. So right now, at this moment, the circuit is has dozed off already, which means right at this moment, I can go to the D pin and go like, oh, I changed my mind. Let's remember 0 instead of a 1. Not happening. Yeah, yeah, I can toggle the D pin all day long and nothing happens. But I can also change the clock pin from a 1 back to a 0 and nothing happens either because it is sensitive only to a rising edge but not a falling edge. So are we good with that concept? Rising edge versus falling edge and how the circuit only does something at the moment of the rising edge. All right? Yes. Yep. 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 Correct. So this is called an edge sensitive D flip flop. So you go like, why do we need two of them? Okay, isn't one of them enough? Well, the sensitivity are different. One is controlling essentially who is supposed to be doing something, and the other one is controlling when it is supposed to do something. Okay? You go like, well, I'm not really quite getting why there's a who involved here. But that's because we're only looking at one single D flip flop at a time. But imagine you have a whole bunch of D flip flops, okay? And then you have some data, but only certain ones should be updated. So that means you need a mechanism to say, hey, you can, you don't have to do anything, you don't have to do anything, but what I want, what I'm going to about to say, you two need to remember that. Okay, that is the enabling. Okay, the EN is for choosing which one of multiple potential D flip flop should be paying attention to the D pin, while the rest we just ignore. But even when you have multiple D flip flops, they're all awake, meaning the EN is on, but you may want to control the timing, okay? Because the moment when the EM pin goes from a 0 to a 1, the data may not be available yet. So you want to have another mechanism to control the timing, which is basically saying, okay, I want you to pay attention, but until I snap my finger, do not write down what I'm saying. Okay, only at the moment that I snap my finger, then you go like, okay, text want me to write down the 0 or 1. So now you have control over both who and also when. Yes. Um, we don't know how long the data is valid, but as long as it is valid during the transition of the clock from a 0 to a 1, we'll be fine. Yep. So when you design a circuit, typically it will be stable or available or correct or valid long before the transition of the 0 to a 1, because otherwise you're cutting it really close. And we don't want to cut things too close. Are we good so far? All right. So after this circuit, okay, so this is basically the last circuit I will basically put in an emulation mode because the next one is a little bit too complex, to really replicate, in a class setting like this. Okay, because if you just scroll down, blah blah blah, those are all basically text-based analysis of the PD, the propagation delay, and the NC, which is node connectivity. So now we have something that is both, okay? And you can see this one is even uglier because it has got three SR latches. It has got SR1, SR2, SRC, and it has two AND gates, AND, not NAND, A1, A2, in order to do this whole thing. It has got three input pins instead of two, but still only has one single output pin. But the name should probably be, looking at the name, you probably can go like, yeah, we kind of expect the number of input pins. Data is still basically the input pin that conveys what do you want me to remember. Okay, so the what is still the D pin. The EN pin is still controlling who should be paying attention, which is difficult to see when we're only looking at one D flip flop. This clock is controlling when do you want me to update. So in this particular case, the mirroring or the copying of the data pin to the Q pin is happening if and only if, okay, the EN is already a 1 to begin with, and we have a transition from 0 to 1 on the clock pin. So you have both the timing and also who should be paying attention. Both of those are present here. Are we good so far? All right. So I would probably say that the circuit that we just talked about, okay, let me go back to LogicSim. So this circuit, you probably also want to perform a PDNC analysis on this one, just a few cycles, okay? You don't have to go through all the cycles that we talked about, but a few cycles will be helpful. This one, contains what we call a transient state, which means a single component or the output port of one of the components can switch states between steady states. So to go from one steady state to the next steady state, one of these components can have its output switching. Okay, and this is the only circuit up to this point that has that particular property. The second thing that you might notice, okay, some of you probably noticed that already, is between N1 and N2, it looks like we have another SR latch. The answer is yes. There's a hidden SR latch here because you can see how the output of N2 is going back to one of the inputs of N1 and how the output of N1 is going to one of the inputs, sorry, of N2. So there is a micro or mini SR latch built into the circuit. The only reason why it doesn't look like a SR latch is because N1 also takes, the one of the input is not from an input pin or the other um, NAND gate, but it is from something that is external over here. So that's the only reason why, this does not look like an SR latch, but it really is an SR latch in disguise. All right, so getting back to our discussion here, the next one is a little bit even more complex. It is the last one, okay? So when you look at this one, the full name of this thing is called a resettable, okay? So you just attach resettable as the first word of the full description. I don't even want to imagine the German name of this thing. No offense to anyone who has German blood, okay, but German names tend to be long, And basically what we describe as a sentence, they use a single word to describe it. So this is called a resettable, clocked, and enabled D flip-flop. Okay, I think I need to consult one of the English professors to find out exactly how it should be named because it has got so many adjectives before the actual noun at the end. All right, so how is this one different from the one before? Okay, you can see they're really about the same. The only difference is before SR1 and SR2 used their output to control SRC, which in this case is direct. Okay, you can see how there's only one wire going from here to here, and you can also have one wire from here to here. Those two wires are broken so that in between we can have this little awkward looking thing here. So now the question is, what is that awkward thing what is it doing? Well, what it is doing is it's paying attention to the input pin that is called reset. So now we can just kind of imagine, what if reset is a 0, okay? So when reset is a 0, then A3 is going to output a 0 as well, because A3 is an AND gate. If at least one of the input is a 0, it is going to output a 0. What about O1, which is an OR gate? The same wire is going through a bubble, which is a negation. So when you see a bubble, it is a negation. So that means the 0 coming from the reset is now turned into a 1 first before it becomes the input of O1. O1 is an OR gate. If at least one input is a 1, the output is guaranteed to be a 1. So that means we are now guaranteeing, okay, when reset is a 0, we are guaranteeing that the S pin is going to experience a 1, the R pin is going to experience a 0. So now you can look up the truth table that we talked about on mm, last Wednesday, okay? So on last Wednesday, we talked about the states of a SR latch. If the S input is a 1, the R input is a 0, it is not trying to remember a previous state. It knows exactly what the output should be, meaning that the Q pin should be a 1 and Q should be, no, take it back, the other way around. The Q pin should be a 0, the NQ or the not Q pin should be a 1. That is quote unquote resetting, okay? That is how we reset a D flip flop that is complicated like this. Is that okay so far? Okay. So once again, why are we making the circuit more complicated? Okay. Before tech, you kind of explain the EN is controlling which one of the D flip-flops should pay attention and update, and then the clock is controlling the timing of when to update. So what about the reset? Why do we need a stinking reset pin here? The reset pin is needed because when you power up a computer the first time, what do you think are the states of all the D flip-flops in your computer? Remember the red lines and the E? Yeah, they're all like that. So do you want to turn on your computer knowing that you only have 1 in 2 to the power of 62 of a chance that it will start the execution of the program to start up the whole thing when you power up? So you power up, nope, nope, nope. Well, try that 2 to the power of 64 times. You might get one time that it will start up correctly. That may not be a good use of your time. No, correction. That may not be a good use of your life, right? So you want to kind of turn on your computer and go like, I want you to start execution at location 0. That's all I want you to do, right? Okay. So the missing link here is this reset pin connects to, now this part is not going to be in the test, but I do want to give you the context of this, just so that you know why we have a reset pin. So the reset pin of almost every single component of your computer connect to a single source of reset. It is called a watchdog circuit. You like why are we bringing dogs into this discussion? Well, because it is called a watchdog circuit. Okay, that's how it is named. So you go like, what is a watchdog circuit then? So this, what follows may sound like animal abuse, but but those are actual technical terms. I'm going to use the technical terms. Okay, so if anyone here is going like, tag, are you promoting animal cruelty? No, these are technical terms. Okay, so when we talk about a dog, it is not a dog. Okay, it is a circuit because we're going to hit the watchdog. So what the watchdog is a timer. Okay, it is basically a timer that can operate on its own without any other circuitry to help it. So you go like, okay, so what is the purpose of the timer? When you first power the computer, as the voltage increases, it's really slowly from zero to whatever operating voltage is expected from your processor. It actually takes quite a bit of time. Okay, so the watchdog, one of the feature of the watchdog is to monitor the power supply to your processor. If it is under a certain threshold, unhealthy threshold, it will hold the reset zero. Is that okay? Okay, so let me say that one more time. When your computer powers up and the voltage to your components is ramping up very slowly, okay, in terms of processor cycle time is really slow. So as it's ramping up, an external circuit somewhere else is going to hold the reset pin a zero, which means nobody is going to do any work because they're all being held in a reset state. They're all just held zero all the time. Is that okay? So the moment the voltage goes, healthy, and after a certain delay, just to be sure, the watchdog will quote unquote release the reset button and turn it from a zero to a one. So you ask, okay, so what does it do when it turns from a zero to a one? Well, if one of the input of A3 is a one, then the output of A3 depends only on the other input pin. If the negated input of O1 is a 1, then the negated input becomes a 0, which means the output of the O1 or the OR gate depends only on the other input pin. In other words, when reset is a 1, then the circuit becomes just a regular edge sensitive enabled D flip flop, just like the one that we talked about earlier. Is that okay? So that's the normal startup sequence of a computer of any kind. It can be your Apple Watch, it can be your smartphone, it can be your laptop computer, desktop computer. Every single computer starts this way. Yes, I would probably measure that in at least tens of milliseconds, if not hundreds of milliseconds. Yep. So it depends on your power supply. So if you have, I know some of you have like a really super gaming rig and you have like 1,000 watt power supply, that's gonna take a while to power up all the capacitors and whatnot. That's gonna take a while for the voltage to ramp up to the operating voltage. Yeah. So you're talking about the physical reset button? Yeah, most computers do not really have a physical reset button anymore because it's too easy for a beginner user to reset when that's not the intention. Hmm. Yes, everything is held in quote unquote a stasis mode. Yep. So that's one use of the watchdog circuit. So once everything is up and running, okay, you go like, woohoo, we can just not worry about the watchdog anymore. Well, that is not the case because Windows, in particularly in the past, is well known to crash to the point where it won't do a single thing. You can press Control Alt Delete and try to do the three finger salute all day long, and nothing happens. Okay, because it is so locked up that it is just not responding to the keyboard, right? So at that point, you can only like cycle power. Now, cycling power is not a problem when it is your watch, when it is your phone, or when it's a computer and whatnot, right? It's not a problem. You just kind of hold the power down for like 10 seconds, and usually that will turn off your computer. Press it again, turn it back on. Hopefully everything is still going to be good. What if you're running a data center? When you're running a data center, you have these racks, okay? The racks are huge. I mean, they're about the same height as this door, okay? And it has computer, 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 computer. So if something goes wrong with those computers, who is going to go into the data center, which is gigantic to begin with, find the one that you need to reset, hold the power button long enough so that it turns off, and then press the power button again to turn it back on again. Can it be done? Yes, but it will cost money. Okay, and you cannot have a density of the racks to the point where a person cannot even fit in the aisle once everything is installed. So you want an automatic mechanism, right? You want an automatic mechanism where the computer itself can detect that it is so stuck in whatever it was trying to do that the best thing you can do is to reset it. Okay, that is where the watchdog timer comes in handy. So the watchdog timer works like this. Okay, the moment the power is good, okay, it will release the reset. Okay, meaning the reset goes back to a one. Right at that moment, it starts a timer. Now, the period of the timer depends on which model you're talking about, what is the application, and so on and so forth. Okay, so let's just say it's half a second. Okay, which is not uncommon. So now the question is, what needs to be not what needs to happen in half a second in order for the watchdog timer to go like, yep, everything is still good. It needs to be hit. This is where the verb hit comes in. Okay, in other words, with that specific watchdog timer or watchdog mechanism, you have to hit the watchdog every less than okay, that's not a good word to use, more frequently than every half second, or at least twice per second. Is that okay? So you basically have to quote unquote hit the watchdog twice a second in order to convince the watchdog that everything is still good. And every modern operating system has a timer interrupt to do exactly that. So when the operating system is still healthy, it would actually go hit the watchdog every, maybe 3 times a second, 4 times a second. Hitting it more often is not a problem, but not hitting the watchdog for half a second or at least half a second is going to cause the watchdog timer to expire. When the watchdog timer expires, guess what it's going to do? Hold the reset line 0 for at least another half second or so. So it resets the whole computer as a result. So the computer resets from the start, okay, and then it will go do whatever it's supposed to do. So that's the whole idea of a watchdog timer and how it relates to the reset pin of a resettable D flip flop. Are we good so far with those concepts? Okay. All right. So with that said, then we're gonna create a circuit like this, a little monstrous little circuit like this. Okay. So the monstrous circuit that we see here. Okay. I'm just zooming out one level so we can see the entire thing. So this is not really super duper complicated because all we're doing is to say, hey, this is the clock, of all of these. So each of these rectangle is a D flip flop. Each of these is a D flip flop, and every single one has a clock, okay, that ties into exactly the same clock on the outside. So this kind of connection where it is dropped in here, it's dropped over here, drop over here, drop over here, and so on. So this kind of topology, okay, which is a way to describe how things are connected, has a really complicated name. It is called a multi-drop topology. I was just teasing you. It's not a complicated name. It's a multi-drop, okay? So you can see how the clock pin is multi-drop, which means every single one of these will experience the same clock. You can see how the reset pin is the same way, okay? It is a multi-drop. Even the EN is multi-drop because the same EN, okay, if you just look at this wire, it goes to the EN of every single one of these resettable D flip-flops. So you ask, so what is not multi-dropped? Well, what is not multi-drop is the data input. So this one connects to only bit 0 of the multi-bit input. This one, okay, just trace it, connects to bit 1, and so on. So the last one, which is this one, connects to bit 7 of the input pin. That's the only one that is not multi-dropped. Every D flip-flop gets its own specific bit from the multi-bit input. Is that okay? What about the output? There's only one output from each D flip-flop. So the D of this particular D flip-flop only contributes to bit 0 of the output pin Q. This one only contributes to bit 1 of the output pin Q, and so on. So when you look at the last one, it is routed to only bit 7 of the output pin Q. In other words, oh, so this circuit is really just the multi-bit version of a resettable D flip-flop, and that is exactly what it is. Okay, it's just a multi-bit version of what we saw earlier. Are we good so far? All right. So this circuit as a whole is also called a register. Okay, so from here on, when we hear the term register, it this picture should pop up in your mind. Okay, so now we can look at this from the object-oriented perspective, which is what does a register do? It can only do two things, okay? It can do two things in this. The condition to do that thing is actually kind of complicated, but it can only do two things. One, it always output the content as an 8-bit number in this case. So a register has an 8-bit value because this is an 8-bit register. So that's the first thing it can do, which is always, okay? It always output its own value. Two, that value can update. It can change. So when does it update? Well, when reset is not asserted, EN is a 1, and clock has a rising edge, then whatever we present to the D input pin here is going to update all the individual D flip-flops so that together the value is updated to whatever the D pin is. Is that okay? All right. So we don't have a whole lot of time, to do anything else, but I can illustrate what a register or how it is useful in a circuit. You have seen this already in the test circuits before, but I never really explained it. Okay, so what we'll do is we're going to go look at a circuit here, and we're just going to call it counter. Okay, so this is what we call a counter circuit. So the counter circuit has a register. So if you want to use a register and you don't want to go through the trouble to make everything from basic gates, you just go to memory, go to register, pick one up, and put it into your circuit. This is the register. This is what it looks like. So a register has many ports. Okay, it has got a D port, but we explained the D port already. That's where the data is coming in. It has a Q port, which is also where the data is going out. It reports the current state of the register. Okay. And what about all of the other ports? This is the EN port. This enabled. Okay. When 0 clock triggers are ineffective, not basically ignored. This one is a little funky because when you look closer, it looks like a little wedge. So this is where the clock pin is. The clock pin is this one, and this is our reset pin. Now, the polarity of resetting is opposite to what I just talked about. This one will reset when this port is experiencing a 0. No, when it experiences a 1, sorry. I take it back. Okay. All right. So it is a little bit on the complex side. So instead of me repeating this explanation over time, you can always go to the library reference. Okay, so let me show you what the library reference looks like. I think we talked about this already in a previous class, but I'm going to show it again. Okay, so you go to the library reference, and then under memory, You just go to register, click on it, and it will give you the same explanation that I just gave you. Okay, so just in case, okay, you want to go back and say, okay, what is it and how do we use it? This is a quick way to refer to it. All right, so now that we have a register here, what else are we going to do? Well, let's go ahead and pick an adder. Okay, so we'll go ahead and pick an adder, which is under arithmetic. This is an adder. Okay, so this is basically the same kind of adder that we have worked out in this class. Okay, remember we worked out a multi-bit adder. So this is the kind of the same thing, except it's internal to the library of Logisim. You don't have to make one. So it has a bunch of inputs and outputs. This is basically our K0 as an input. This is our X as an input. This is our Y as an input. This is Kn, okay? N in this case is 8, so this is K8. And this is sum or our S port, okay? So it's basically the same thing as what we have talked about, except, you don't have to work out the details, okay? All right, so we're gonna have some fun with this. And then we just say, okay, I will take the output of a register to one of the two inputs of the adder, X in this case. And then the Y is going to be a 0, excuse me, a 1. So I go to wiring and specify a constant like this. And just say this is a 1, but it is an 8-bit 1. So I have to specify a bit and then change the value back to just 1. There we go. Stash it here. I want K0 to be 0, okay? It doesn't have to be, but this is one way to specify a 0. So now specify constant, change the actual value of the constant to a 0. It is a single bit already, so it will work just fine, like so. All right. And then I take the output and then I put it back to the input of the register like this, and nothing happens. It's like, what? Isn't this whole thing supposed to be adding one to the register the whole time? Because, hey, look at this. The output of the register goes to one of the two inputs of the adder. The two inputs of the adders would be 0, 0 on one, 0, 1 on the other one. And since K0 is a 0, the output should be a 0, 1. Well, let's find out whether it's 0, 1 or not. It is. Then what is happening here? Why is nothing happening? Because it's not enabled and the clock is not doing anything. So it is just not doing a single thing. All right. So what do? Well, we just hook up a whole bunch of input pins so we can control these individual input ports. So we hook up one over here, and then we hook up this one to the clock. Oh, okay. There we go. And then we'll have one more for the reset, because if I want to demonstrate how to reset, this way I can do it too. All right. So still nothing happens because enable is a 0 instead of a 1, and the clock pin is not transitioning in any way. That's why it's not doing a single thing. So if you wanted to do anything, first of all, you have to enable the transistor. I mean the resistor. No, register. Okay. So you enable the register, and nothing is still happening because the clock pin is a 0. Remember, the clock pin has to go from a 0 to a 1 in order for, at that moment, for the register to change the output to the input. So this is the important part, okay? As soon as I click on this pin here, you can see how the content of the register changed from 0, 1, which was the input of the D, to whatever the output of the adder was at that time. But everything has changed now. Because now, if you poke the wire, the output of the register is now 0, 1. The output of the adder is now 0, 2. But nothing is happening to the content of the register for one reason. The clock pin is now static as a 1. It is not transitioning from a 0 to a 1. Okay? So in order for this circuit to do anything, you're going to have to go back here and toggle this pin. Now, if I click again, it will go from a 0 to a 1 again. So this time, the register will go from 0, 1 to 0, 2, 3, 4, and so on. Okay? So this is the circuit of a really basic counter. Every time you have a rising edge on the clock line, it just counts up by one. Okay, so if you go back, okay, I know some of you might still have those files. So if you go back to the circuit tester from week 2 or 3, or even week 1, I think. So if you go all the way back, you will actually see this circuit in the tester circuit, because I need something like this in order to move on to the next test case, okay, which is controlled by ROM, which is a little bit more complicated than I need to go through right now. Are we still doing okay so far? All right. So this is basically the simplest what we call a clocked circuit that demonstrates something. It's called a clocked circuit is because when the clock is stationary and it doesn't clock anything, it doesn't move, then nothing happens. It relies on a single clock in order for things to happen. Think of this clock as a metronome or the conductor in a of an orchestra, right? So, you know, what happens when the conductor says, "Oh, emergency! I need to go to the bathroom." What happens to the rest of the orchestra? Nothing happens. Okay, all the musicians, all the violinists and flutists and whatnot, they just go like, "Oh, okay, we just rest, do nothing, absolutely nothing." That's what a clock is. Okay, so playing music is a clocked activity. Okay, because everything depends on the basic beat. And your computer, your processor, also has a clock that dictates the timing of everything. Are we doing okay so far? All right. So now I'm moving the topics a little bit out of order, okay, because um, I don't have a lab for today, but I don't want to waste that time either. So the lecture is going to eat a little bit into the lab time. I promise you it's not going to be like the whole lab time, but I do want to move a little bit into the lab time so that in the next class we'll be ready for the lab and also gives you more time to kind of absorb the content. So do you want to take a break first before, because I can just kind of continue the lecture until maybe 12:30. Do you want a break first, or do you want me to just keep going? Just keep going? Okay. You guys are good for that? Nobody needs a quick recharge? My watch actually has a metric called body battery. So it goes up when I sleep, and then when I work, like doing stuff like this, it will kind of drain and it would start to discharge. And there are many days it would get down to zero at about 4 p.m. and I will keep going for another 2 or 3 hours. All right, so let's keep going now. All right, so for this class, I want to show you. Where's my Logisim? Oh, right, the last one now because it's now hidden. Okay, so I'm going to file open and nope. Okay, so I have to go back to retrieve that. Go to documents, CISP 310, go to processor, and this is all right. So this is what you'll be using until the end of this semester. This is your processor, okay? So it has a lot of stuff, okay? I will explain all the components, okay? I promise you, I will explain all the components. So we have multiplexers, demultiplexers, and so on. Now, I'm not going to do it today, okay? But a multiplexer and a demultiplexer, in terms of railroad technology, they are just switches. That's all they are, okay? Which of the inputs connect to the output? Pick one, okay? Which one of the output does this input connect to? Pick one. And that's all they do. Okay, they're really simple devices. They are kind of like array indexing. Okay, because you're basically saying, okay, the array has multiple things. Which one do you want? So it really is doing the square bracket thing when you're using array indexing. That's all a switch is. Okay, it's just that when it is presented like a hardware thing, it just makes the circuit look really horrendously complicated. So that's that, and then it has got a ROM component here. Okay, so a ROM component is kind of like a book where you cannot change the content, but you can say, okay, which page do we want to switch to, and then the output will just show you the content of that page. In other words, huh? No, it is not a stack. So you can look at ROM as an initialized array in C++. So the content comes with it. It is a const also. You cannot even change it. But otherwise, it is like an array. Okay, you can say, okay, I want item 265, okay, or the item at index 265, and it will give you the content of that page. Okay, so from conceptually speaking, it is not super difficult. And then we have RAM on this side. Okay, so this is the other major component. It is called RAM. So RAM is also like an array, but it is rewritable. Okay, in other words, you can say, okay, I want to change a bracket, 265 to a new value of 16. Okay, so with ROM you cannot update. With RAM you can. So conceptually, that's basically what they are. So what do we do with this whole thing? Okay, that's the thing. That's the idea. What do we do with this? So what we're going to do with this whole thing is we can write programs and we'll run on this processor. Okay. So I will demonstrate quickly and then we'll start to introduce the basic components in just a little bit in today's class. But as I promised, okay, I'm not going to move beyond talk beyond 12:30. All right. So we'll go ahead and take a look at a particular program. So we'll call this test.ttp-asm. So the TTP-ASM is not a standardized extension. It is simply saying it is text toy processor assembly. Okay, TTP-ASM. Okay, so I'm gonna write a really simple program here. Okay, start with a no op, which is literally just saying do not do a single thing. You don't have to copy this. We'll get back to this at some point. Put a label L1, LDI. Oh, I can do the LDI earlier. LDIA with some value, say 5. L1, decrement, uh, decrement A, and AA, JZI to L1, and put a halt instruction here. So this is a really simple program that has a loop. Um, so the, the focus is not what the program is doing. The focus is what are the processes, what are the steps to make use of that processor. Okay, so this is how you write some program. Okay, and then I have a pretty cool tool to do this, but I'm not gonna do it that way. So I'm gonna do the long way because I want to expose the whole tool chain. So what I'll do next is to put this into my clipboard. Mm, This is how I can put the content of the text file into the GUI's clipboard, so I can paste it into the browser. And if you're thinking, oh man, I wish Windows can do that, then switch to Linux. I will show you guys how to do it if you want to. All right, so we go to a Google Drive, okay, and you're gonna know exactly where to find all this stuff too. So today I'm just showing you kind of the whole process so that you have some idea of what we'll be doing. So we go back to this, go to the share folder, go to the processor subfolder. Okay, there we go. So in here, there is an assembler. Okay, so this is called the assembler. So an assembler is essentially kind of like a C compiler because your C code cannot be understood by the processor at all. Okay, so you need something to translate your C code into machine code that the processor can understand. Okay, So I simplified the whole process. Okay, there's actually a whole bunch of stuff that needs to happen in between, but we'll just say that the C compiler cranks out machine code that your processor understands and can execute the code. This is kind of a very simple C++ compiler, except it doesn't take C code, it takes assembly code. So the code that I just wrote and put into the clipboard is supposed to be processed by the assembler. So you double click on this and you go to the source tab. The first thing you notice is this does not look like a computer program. It is a spreadsheet. It looks like a spreadsheet because it is. So I basically abused a spreadsheet and turned it into an assembler. I don't think it takes a PhD to do this. You just need to have time. So now you just take out whatever code was here, okay, paste the new code in, wait a little bit, let it bake, okay, just like those infomercial things. So now it's all done, right? So you just make sure that there's no error message over here because otherwise you need to check it first or deal with it first. You go to RAM file, okay, it gives you some really awkward hexadecimal digit thing. That is the content that needs to go into RAM in order for the program to run. So now you go through another process here. You go to File, and then you go to Download. You download as a TSV or CSV, but I would choose CSV. Both will work, but this is just my preference. So now you go slash test, whatever .csv. I just don't like long file names, so that's what it's going to save. So now we go back to Logisim, which is kind of one of this one here. So we go to the RAM component here, right click, go to load image, and then specify the path to that file that I just saved, which is in the temp folder. And you can see how the content of RAM has now changed. Okay, this is Varnum architecture. Okay, the behavior of the program is specified by the content of memory. So it is, I, I, I think, I hope this method makes everything visible. Because otherwise, it's just a concept, right? It's like, oh, okay, the content of the behavior of the program is controlled by the memory content. Okay, conceptually you get it, but now you actually see it. So now we run the code, okay, so we can animate stuff a little bit, so you can see how register A is changing, as we run the code. So I'm going to go to simulate, but I will reduce the simulation frequency down to a point where we can visually see changes happening to the registers. Not just register A in this case, you can also pay attention to, okay, I guess we have to zoom out a little bit. Oh, by the way, the zoom control is here. It is not exactly where you normally would expect it, but this is zoom control. So we can zoom out just a little bit so that we can see how register A is changing in binary numbers. The program counter is changing in hexadecimal. The instruction register is going to change. So all of these are visible as we run the program. So now we go to simulate, and then we just go like, okay, let's go. So what text enable do is the clock is basically now automated. I don't need to go in and go like click, 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 click to see the program run. I can just do this, and then the clock will cycle between 0 and 1 automatically. So you can now see how register A is now 5, 4. Mm, uh-oh, did I not write the code correctly? Yep, I did not write the code correctly, so that's why it's stuck. It's already done, okay? So the way I know it is done is because the halt pin is a 1. So when you go all the way down, there's a halt pin here. So when the halt pin is a 1, it means the program is finished. So that's because of me, not writing the code correctly. But that's how you run the code, okay? So there's a quicker and easier way to run the code, but this is how we'll start to do it at the beginning. So do we have any questions? Yes. You mean the assembler? Maybe a summer. Yep. Hmm. No, no, that is not your job. However, however, for anyone who is interested, anyone who's interested in how this assembler works, it is open sourced. So that means you can actually go to the assemble tab and find out how you can figure out all of these things here because they're all based on equations of certain kinds. Okay. The whole thing is also, well, I mean, it's quote unquote open source because all the formulae are open. You can actually click on stuff and find out, okay, how does it work? You also need to go to extensions and then you go to apps script because some code cannot be done using just the spreadsheet formulae. So I do have a kind of supplemental stuff here, with um, that's JavaScript code. So it is basically supplemented by some degree of JavaScript code. So for anyone who's interested, you can look into it. Nothing here is proprietary. I'm not selling it. I don't have books, that I need to protect or copyright. So you guys are more than welcome to kind of check out all of these things. So there are a few other things I need to point out, okay? And before we move on, to the actual components. The RAM component here, okay, so let me just click on it so you can see the properties. This RAM has only an 8-bit address bus, which means it only has 256 locations. And then when you look at the data bit width, it is also 8, which means each location is only 1 byte. It has 256 bytes to store your program, the stack, all your variables, etc. That's your entire thing. Huh? Well, there's no heap, in the code that we're going to write, but if there is the heap, it also has to fit in the 256 bytes. Oh, no, no, this is way below that. Yeah, this is way below that. Floppy disks, are still in kilobytes. They're in hundreds of kilobytes. Even the small, the low density ones, they're yeah. This is like 200. This is 256 bytes. Yes, yep. It doesn't take someone too long to write all the way from 0 to 255. I'll put it that way. Okay. So now the question is, what can we do with this little stinky processor? Okay, you can actually write the algorithm to solve the Tower of Hanoi using 256 bytes for all the instructions that you need and also a reasonably large stack. I think it works up to like 6 or 7 disks. The limitation is time. It's going to take a long time to solve a 7 disk Tower of Hanoi problem. Do you guys know what I'm talking about? Tower of Hanoi? Okay, some people say and some people. Okay, we'll go. Yeah, go ahead. Mm-hmm. Yep. Yep. So there's different origins as to where this puzzle came from. There are some references to this is a Buddhist, or religious kind of thing, where the monk has to follow the rules. And I cannot remember the number of discs. It's not insanely high. The number of discs is not insanely high. So the idea is, you have a stack of discs, okay, on 3 different poles. They start with one, so there are 2 rules that you have to use when you're trying to move the disks. You can only move one at a time. Okay. The second one is you cannot have a larger disk on top of a smaller disk. And those are the only 2 constraints. And the idea is you want to move every disk from the leftmost pole to the one that is all the way to the right hand side. The one that is in the middle is kind of, you can look at it as your buffer. Okay. So those are the only rules. Sounds pretty simple, right? Well, try to do it yourself. With only 3 disks. I know, that's only for 3. it will take 2 to the power of n minus 1 moves for n disks. So you go like, that doesn't sound too bad. Yes, yes, 256 bytes will both specify the code as per von Neumann architecture, right? Because the code has to go into RAM, but it also stores the stack that you need in order to get the algorithm to work, because it's a recursive algorithm. Did I just say recursion? Recursive? Yes, I did. So we will be looking at quite a bit of recursion in this class. So were you guys introduced to recursion in CISP 360? Okay. No? Okay. So you will be introduced to recursion in this class. So in CISP 360, recursion has a, I would say, mythical property to it, right? It's like, how can this possibly happen? I can see only one variable in the function. Why do you say that there are multiple versions of the same variable? I mean, no matter how they try to explain it in CISP 360, it is difficult because the key to understanding recursion is the understanding of a stack, which we'll be talking about. Once we understand the concept of a stack and the call frame, then you guys go like, oh, so that's exactly what is happening in recursion. So that's one of the objectives of this class is to demystify recursion. Okay, because for anyone who claims that I understand, how functions work, but I have no idea how recursion works, then my response to that is you really don't understand how functions work. That really is the limit test of whether someone understands recursion or not. Okay, so that will be a kind of like a side focus of this class, but nonetheless an important one. Okay, so that's what we'll be doing. Okay, is to use that little processor, that doesn't seem, it's not impressive in any way in terms of the amount of resources, but we'll be writing some interesting C code that will be translated into assembly in order to run it here. Now, the other thing that's kind of cool about this processor is you can stop the simulation anytime you want. Okay, just stop ticking. Then you can actually understand how each part of the processor interacts with the other parts of the same processor. Okay, so it gives you an inside view of what is inside a processor. The best analogy, if you want to walk away with something, is like, okay, I cannot remember a single thing of this entire lecture. Give me something I can actually remember. So the best analogy of a processor, or at least the level at which I'll be explaining it, would be it is kind of like the Solder's Island in Thomas the Tank Engine, and we'll look for the island. Okay, come on, give me the island. The island of Sodor. There we go. So the reason why this is helpful is because, oh, there's an actual island of Sodor. Interesting. All right, so when you look at the map, okay, when you look at the map, no, I'm not signing into Facebook. Dang it. Hmm? No, I did not. Pinterest, no. This will work, I think. Yeah, it works okay. All right. So imagine the processor is the island of Sodor, okay? And the island of Sodor has functions. Okay, so certain ports or seaports, they're supposed to take in cargoes from ships and whatnot. Okay, your raw material, and then you have factories on the island that would take all the raw material, make something out of it, right? And then you also have to ship. You also have to move all the products, the finished products, to another port or to the shopping mall or whatever, so that you can sell that stuff, right? So now you have trains, okay? You have trains on the island that are responsible of moving things from one station to another station. Some of those stations are registers. Some of those stations is RAM, some of those stations are ROM. Those are the individual components, either to provide content or to consume content or to transform content in the case of the ALU, which is the logical, arithmetic and logical unit. It does all the calculations. Okay. So if the stations are registers, RAM, and ROM, then what are the tracks? The tracks are the wires, okay, making all the connections, okay? But then you might end up with a situation where you have multiple tracks coming in to the factory, okay? Because sometimes you need incoming trains to drop off your raw material, other times you need outgoing trains to go to the port or go to um, you know do some more additional processing, packaging and whatnot, right? So you can have multiple tracks coming in and multiple tracks going out. So now you have to control. It's like, okay, we need these two tracks. Out of these two, I need to connect to this one because now we just want to take the this material A to the warehouse, and then when this is all done, then we'll go to material B and so on. So how do you control which track connects to the port of the factory? A switch, a railroad switch. Yep. So we can take a look at a. It doesn't have to be binary. It can be multiple. Okay. So we'll take a look at a railroad switch. Okay. So you're correct. Okay. Most of the time it is binary, but what happens when you have a hierarchy of these switches? So I'll just kind of draw it on the whiteboard just so that we can get an idea, right? So let's say you have one switch here, and it is in fact binary. Okay. What if you attach another switch over here that is binary, and attach another switch over here that is also binary? Now you have four destinations or four things because you have. So let's just say this is the incoming. So now you have four destinations that you can switch to. Does that make sense? Because we can quote unquote stack switches. Stack as in arranging in a hierarchical way. All right? Yeah. But you can also extend this and go like, oh, what if we have three levels of switches? Then you can have one single incoming, and now you have eight outgoing. Is that okay? So that's basically switches. So in the circuit diagram, okay, so we're going to come back and look at this in a much more formal way. This is a demultiplexer, and a demultiplexer means you have one incoming track. In this case, it has four possible outgoing tracks. So in this case, we have one incoming on the left-hand side, and it has four out of four, only three are connected, okay, of its outgoing tracks. So now the question is, but how do we specify which track, right? It's got one in, and one of the four is supposed to be connected. So that would be the job of whatever is connected to the gray dot. So the gray dot in this case is it tells you exactly what it is. It says which one of the output is supposed to get the input. So that would be equivalent to there's a lever here, there's a lever here, there's a lever here. So this is the first level lever. These two are both the second level levers. So in order to switch from 1 to 4, you need two levels of levers. Does it make sense? That's basically it. That's the whole story of multiplexers and demultiplexers. It's really that simple. It's just a way to say, hey, you got a lot of stuff coming in, and there's only one connection to you. Which one is supposed to actually make the connection? Just select one. Okay. And then we also have hmm? Oh, okay. Gesundheit. What does that mean? What does Gesundheit mean? Yep. It's not blessed. It's actually a lot less religious. I think it's just good health. Yep. All right. So this is the register bank. So inside the register bank, we just have a bunch of registers. So basically, you have four registers, and then four between the four registers, you have to say which one becomes the output of here, which one becomes the output here, and with the input, which one is supposed to receive the input. Okay, that's the job of the register bank itself. And then we have the ALU, which looks awfully complicated. Okay, and its only job is to say, okay, we have six operations that we can perform with room for two more, okay, but I only use six. That's all that I need for this class. We can add, we can subtract, we can right shift, we can do a bitwise not, which is one's complement. We can do a bitwise and, we can also do a bitwise or. That's it. That's those are all the things that we can do. But in this particular circuit, we also have an overflow. So if you look at this subcircuit over here, not this one, but this one. So this subcircuit is actually how we compute overflow based on the discussion of binary comparison. So all the stuff that we have been talking about, adding, subtracting, comparing, all that stuff, they are all done inside the ALU. The ALU is responsible for arithmetic and logic operations. Okay, that's the ALU. And then you have RAM, that is responsible to store everything, including the code of the program and also the stack. So what goes into the stack? Every parameter, every local variable goes to the stack. How many of you wrote programs in CISP 360 using global variables? Okay, well, I know it's gonna suck, but I'm gonna say anyway. Ew, ew, global variables. You okay? So this is just a little preview of what will happen in your career. Do not use global variables. If you can avoid using global variables, don't use global variables, with one single exception: constants. Okay? So if you have constants, those can be global. Hmm? Yep. Well, I mean, constants are basically establishing which identifier means what value, right? You can use enum for that too in C++, but basically constants can go global. Yep, yep. Not just constants, variables being global. Yep, variables being global. Yep. They might have done that for efficiency because passing parameters is actually costly or bad efficiency, not good efficiency. I see. I see. Okay. So in this class, we'll be using a style of programming where we do not use global variables at all, like zero use of global variables. So that means all the variables live on the stack, okay, because they're all local variables, which is interesting. Okay, so we'll talk about how we store variables on the stack and how that relates to recursion. Because without this, a programming language cannot handle recursion. So recursion counts on local variables and parameters being stored on the stack. So we'll talk about that. We'll talk about structures, okay? In this class, we'll talk a little bit about arrays. So basically, we'll start with C code using all of those constructs and pointers, okay? Lots and lots of pointers. I think I did warn you guys that we'll be using pointers. Yep, we still have a few weeks before we actually get to the real pointer stuff, but we will get there, okay? So we'll talk about pointers. We'll talk about a member of a structure that is pointed to by a pointer that in return is also pointed to by another pointer. Double dereferencing and then getting to members of structures which turn out to also be pointers. And Mhm. Nope, nope, no, 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 no. Pointers are pointers. A double Yeah. So yeah, but double pointers sound really awful. We'll see stuff like this. Okay, I'm not trying to scare people away. Okay, so you have a double pointer, and then whatever it dereference to, it will point to a certain member, which in return can also be a pointer. Then you can also point to something else. So we can potentially get into syntax like this. Okay, so now the question is, do you know how to interpret it? Okay, can you describe what the expression is trying to say in this case? So I'll give you my interpretation of this. Okay, okay. So we are looking at member n of a structure that is pointed to by member m of a structure that is pointed to by the pointer that is pointed to by PPTR. That is how we see it. Okay, so I'm making some assumptions here that you have learned all this in CISP 360. And yes, and this is also why taking 400 first sometimes is beneficial to this class, but it doesn't have to be. Okay. Oh, 360 and 400 at the same time? They let you do that? Oh, okay. 310 and 400, yes. Yeah, those two can be at the same time. But it's yeah, okay, that works. Okay. So this will give you, an additional way of looking at pointers and structures that might help you actually in 400. Yep. All right. So this is something that we'll be getting into, and it'll be so a statement, an expression like this will be inside a recursive function. But those are all orthogonal concepts. In other words, one really does not make the other one more complicated or less. They are simply in different dimensions. Okay, so we'll talk about all of those things. So this means if you have any concepts in CISP 360 that you feel that I feel a little bit unsure about those concepts, this would be a good time to kind of brush up on those concepts. If you need some help, okay, if you go like my professor never talked about these things, come to me, go to my office hour, and I'll be more than happy to kind of help kind of put everything back into what you need to know. Is that okay? Well, these things are kind of use it or lose it too. So if you have, like a whole or 2 semesters between taking this class and the last actual programming class, maybe 360 or 400 or 430, it will get difficult to kind of get reacquainted with these concepts. It also sucks for people from Sac State. I'm not sure, whether there are anyone here in this class from Sac State. The reason is in Sac State, they don't teach C++, they teach Java. So the problem with Java is Java has no pointers. It has references, but not pointers. Those two are not exactly the same. So that's why, but those people, okay, people who take this class because the same class at Sac State is too impacted, probably not happening in this class, but possibly in my other class. So those people, I cannot tell those people they cannot take assembly language because Java is our 401. In order to get to 401, it has a prerequisite of 360. So by by that kind of reasoning, someone who has taken what is equivalent to our CISP 401, which is Java, should have everything that needs to be known from CISP 360. But that is a faulty reasoning because it is only implying that certain things will be known if somebody knows Java already, but not everything from CISP 360. So this is going back to the necessary condition versus sufficient condition thing. So whoever used the curriculum to say that, well, but this person passed this class already. They by implicitly this person would know everything about all the prerequisite classes. That's faulty reasoning, but I cannot change institutionalized faulty reasoning Okay, so if there's anyone here with only a background in Java, you probably need to understand or spend some time on pointers because that's what we'll be talking about in this class. Okay, all right. So I did say 30, but I think we are good now. Okay, I think I have introduced enough so that you guys can have a general idea of what we are going to do until the end of the semester. All right. I'll see you all on Monday and have a nice weekend. Points to. So the Yeah, I'm not even sure whether it has its own name, but basically, if you have a pointer that is to a structure and you have a member of the structure that it points to, this will access it. So this really is exactly the same thing as dereferencing the pointer first, so it's a structure, and then accessing member M. These two are basically the same. It's a shorthand. A structure is a class, except everything is public. But otherwise, yeah, it is a struct. Structure is a struct. Yeah. Okay. Yes. So P is an instance of a struct. It's an object of a struct, or it's a variable that is a. Oh no, I take it back. It's a struct pointer. So P is a struct pointer. M is a member of the structure that it points to. So this allows you to access. This is retrieving member M of the structure that is pointed to by P, which is the same thing as doing this because this is just looking at things from the opposite direction. P is a pointer to a structure. Asterisk P is a structure. And now with a structure, I can access member M. No. P is storing. Okay, so the best way to illustrate it is to say we have a struct X um, int M int N. Okay. And then in the actual code, you have X struct X P and X. X is not. X is not good. We'll make it W. Okay. So now you can say W equals to, oops, not the other way around. You can say P equals to the address of W. And now you can say P points to N gets 20. So uppercase X is the name of quote unquote the class or the struct, and it is used to make a pointer and also an actual object here. So W is an actual object. So when I need to, so P is now the address or the pointer to W, and if I want to change N of W, I can now say, oh, the member N that is of the structure pointed to by P, let's change that to 20 in P. So P is the address of W. So P points to N is referring to basically the same thing as the member N of W. I'm doing this because I want to illustrate pointers. Yeah, this code does not require the use of a pointer, but this illustrates how we can use a pointer. Uh-oh. When you say that, it's like that means the concept is not well discussed in your CISP 360. Okay. Yeah, because usually they run out of time at the end of the semester. From which college? If you This one, we don't have a fully online C++ class. It's hybrid. It was fully online? Ooh, I did not know that we have a fully online one. Mhm. 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 Right. Mhm. So they don't combine. So they have not combined the two concepts, address of, reference, and combine that with the concept of structures. Okay. All right. Okay. I know. 400 is mostly stuff like that. Mhm. Yeah. Yeah. Nice. Okay. Yep. Yep. Cool. Mhm.